Hello and welcome back. This is Matthew, and today we are going to look at the Data Description Specification, or DDS language, in IBM I. This is used for a couple of things. Today we're going to use it to define physical files, which most of us would think of as database tables. So let's sign in. I'm going to change my current library to my M. Wilson library, just so that I know where all of my files are going. And as a quick recap, we saw in video number 1 that using the SQL interface, I'm able to do things like create a table, maybe a table full of people. People might have an ID, a first name, and let's say a last name. So that creates the table. We can do things like select star from people, and we can see that the fields we created in people are there. So nothing too surprising there. However, the SQL functionality, the SQL interface, is not a standard base feature of IBM I. It is an added price option. And SQL hasn't always been available as a query language in the old AS400 OS, is my understanding. So what was the traditional IBM I way of defining these tables to then be used in business applications? And the answer to that question is the DDS language, Data Description Specification. So we'll use DDS to describe a physical file. And just as a reminder, since we created that database table called people, we have this people physical file. So this is the actual table storage for that table that we created. So the other way we create physical files is by describing them with DDS and then compiling the DDS member or file, which will create another physical file for whatever kind of data we described with DDS. So to do that, I'm going to create a source physical file. Remember, source physical files are where our source code lives. And by convention, DDS source lives in a source physical file called QDDS src, although you can name this whatever you want. It has no actual meaning to the system. So we created QDDS source in library in Wilson. We'll use the Programming Development Manager, work with members, and we'll use that QDDS source file we created. It's not in the demo lib, it's in my current lib, which is set to M. Wilson. So I can either type star curlib, which is that symbolic name for my current library, or I can just directly type the name of the library, but we'll do it this way. You can see that did in fact select M. Wilson. Now I just created this file, so it's empty. We can go ahead and hit F6 to create a new member. And what kind of database do we want to create? I like astronomy, so we'll go with an astronomy theme, and we'll start out with a table to hold the catalog of Messier objects. These are particular objects in the sky that an old guy named, I believe, Charles Messier found and cataloged and described over time. So let's name it after him. And our source type here is going to be PF for physical file. We're using DDS to define a physical file. And we can give it a description so we know what it is later. We can say, table to hold Messier catalog objects. And here we are in the source entry utility, our programmer's text editor. Now, DDS is a positional language. So the syntax is entirely defined by what column you put the various keywords and identifiers in. So we have some help up top here. We have the T, so this column is where the type goes. The name of the field goes here. The record length goes here. The number of decimal points for the numeric fields goes here. And then any extra keyword functions go in this portion of the file. Now, it's kind of difficult to do that. So we saw the prompting feature in video number 2. And in this text editor, I can insert lines, and that lets me start typing in lines here. But I can also, I'm going to delete that line. We saw we can hit F4 to bring up prompting on a particular line. But if I know I'm going to be entering a lot of lines that I want prompting for, I can use the line command IP for insert with prompting. And since this knows that we're in a DDS file describing a physical file, it will help us with the correct syntax for this situation, which is pretty useful. So at this point, it's just kind of like SQL, but a different format. I'm simply going to describe the fields that I want in this database table. And the first thing I need to do is name the record format. So what am I going to name this record format? Well, it's arbitrary, but we can call it Messier record, perhaps, an R for record. And that'll be the first line of our file. That just goes on its own. And now I list my fields. So Messier objects have a number. So look, we can call this field Messier number. Length, this is a right justified field, so I need to go over to the end of the field here. Messier numbers, 3 digits will be able to contain it. Data type, again, I can hit F1 in the data type for help. I can hit F20 to make this a bit bigger. And here we can see all of the data types that are supported in DDS. I have not been living in the IBM world for very long, so the whole zoned and packed decimal thing seems a bit weird to me. For something like the identifier, I'm going to use just a binary field. So we will use a binary field that allows up to 3 digits. And in this case, these are whole numbers, so no decimal positions. And that's all I need to enter to define this field. So I'll hit the enter key. And you can see that it placed all of the elements of the syntax in the correct columns. So A, I think, is just there for historical reasons, identifying this as a physical file DDS source. I believe that's technically optional now. So if you leave that blank, nothing goes wrong. We see our field name under that name position. We see the record length, right justified is 3, and the type is B for binary. And then again, decimal positions, right justified 0. And we didn't need to use any of the other fields. So we have a field or a column named Messier number. All right, what else can we track on these? Most of them have an entry in the NGC catalog, so maybe for cross-reference, we'll allow that to be a 4-digit binary number with 0 decimal places. And they may have a common name, like the Lagoon Nebula. So that will be a text field. We'll give that maybe, I don't know, 20 characters of alphanumeric or character data. We don't put in a decimal position for character data. We can talk about the distance. Whoops. The distance, and that'll be measured in light years. So maybe dist ly is a good field name. Now this will have decimal positions, and it could be a pretty big number. Some of the Messier objects are actually other galaxies, up to maybe in the hundreds of millions of light years away. So we could make this, thousands of light years to save a little space, but we'll just go direct light years here. And let's give ourselves maybe 11 total digits of, and here I'll use that funny zoned decimal, but we'll leave ourselves maybe 2 decimal positions. So 11 digits total. 9 of these are going to be the whole number part, followed by 2 decimal positions. So this length is inclusive of the decimal positions. So that will give me 9 digits, followed by a decimal point, which doesn't count in the length, followed by 2 more decimal positions. So I can have tenths and hundredths here. Great, I like that. We can record what constellation the object is in. There's some standard constellation descriptions that are 3 letters long. So 3 character bytes there. We can track things like the magnitude. And again, we can say these could be, up to maybe 11.2 all the way down to 0. So we can give ourselves 3 decimal digits, one of which is a decimal point. So I can have 3.2 or 10.2. Perfect. And last but not least, where in the sky is this? Now, right ascension. This we're going to give ourselves, it can be up to 24 for a right ascension of 24 hours, 0 to 24. But then hours and minutes and seconds can actually make you need several decimal places to represent right ascension if you're representing it as a decimal number. So we will give ourselves maybe 11 and make this zoned decimal. And most of those 11 we want to use for after the decimal point. So we'll say 8, right? Because that leaves us, well, that leaves us 3 whole number positions, which we don't really need because it'll never be over 24. So we can give ourselves 9 decimal positions. And then finally, declination. And that, similar to right ascension, is going to be 11S9. All right, so I'm all done with that. I'm going to hit enter again to get out of the prompt. I'll page up so we can see our whole file. So you can see this is pretty straightforward once you know kind of the abbreviations and how to use the prompting to get everything in the correct position. We've listed out several fields or columns in our table. We've given the lengths, the types, and in a couple places, the fact that we want some decimal positions on these things. We haven't used functions yet. We'll talk about that briefly. And we haven't, if you think about SQL, you'll usually make a primary key on the table. We haven't really done anything to indicate a primary key. So for primary key, let's use the Messier number. Those are unique. They uniquely identify the entry in the catalog, and it's what we'll generally use to look up a particular object. So to make that a key, we can add an extra line here, and I'll prompt it, so IP. And the name type in the key will be K for key. And then I just repeat the field name that I want to set as a key field. Hit enter there. So now my Messier number field is my key for this table. Additionally, to make it a primary keys must be unique. And the way we do that in DDS is the first line of the file, we want the function unique. Now again, I could hit F4 and prompt this and type unique into functions, and it'll end up in the right place. But since I put it in the right place under the functions column header here, it knows that that's the function. And so unique is a file level function that just means the key must be unique in this table. All right, turn off the prompting here. So unique key, Messier number. The record format name is Messier record. This ends up getting used in some programming languages to refer to this record format as opposed to the table itself, which we'll probably just call Messier. And then we have our description of our fields. So this is probably clear now. I am at the point where I'm just repeating myself, I think. So we will go ahead and hit F3 to quit. Get rid of that selection there. And because we made some changes, yes, we want to create or change the member. So I'll just hit enter here. And we now have our Messier physical file source in the QDDS source file. Now we haven't actually created the table yet, right? If we go start SQL from here and say select star from Messier, it'll say I have no idea what Messier is. Okay, fair enough. Because all we've done is write the source code to describe that table. So now that we've done that, we can compile it with option 14. Hit enter, and it compiled successfully. File Messier was created in the library M. Wilson. Now, even though we didn't use SQL to create this table like we did for people, we just described it with DDS and we compiled it. if we look at our work with objects, for all objects in the Emulsion library, in addition to that people physical file that we created through SQL, we also have our Messier physical file that we created by compiling the DDS description of that table. And as you'd expect, if I go back to SQL, and I can go up to the select star for Messier line and F9 to retrieve that, now when I run that command, it works. And even though we didn't use SQL to describe this table, when I run a SQL operation like select star on it, you can see we have all of those columns we defined. And there's more to the right here, so we can hit F20 to go over, and we see our magnitude, right ascension, declination. Okay. Now, since we're nominally not using SQL here because we didn't pay for the SQL option, we have the question of, well, how do I actually get data into this file, work with this file, etc.? And really the answer is you write a program that is then your front-end program for end users to use to work with data in your data files. But as a developer tool, there is a utility called the data file utility. So I'll start the data file utility. And this lets me create quick and dirty sort of test or developer programs to work with data files. You can actually create a DFU program and it will write a program for you, compile that program, and you'll have an executable program that you can run over and over to work with your data file. Or you can just have it create and run a temporary program for you, and then that program is gone when you're done working with it. So that's all we need to do now. So just to be quick, we will update data using a temporary program. I give it the physical file, in this case Messier, and the library, which we created in M. Wilson. And there's probably not something called books in here. Generally for data files, you can just use the first member, or you can hit F4 to list the members. In this case, there's just one member, Messier. This is kind of confusing. So the physical file is Messier. But remember when we create source physical files, like that QDDS source or my QC source, where I put C source code, the Programming Development Manager lets you create several members, basically different source code files, inside that one file. Those are the members. And physical files, even though this is just a data physical file, can also have multiple members. Now, I'm not sure what kind of real-world use this has. I'm guessing it's not heavily used since star first appears to be a reasonable default. But you can have two completely separate sets of data with the same record format because it's in this Messier physical file, which was defined from that Messier R record format. And there's ways to alias these into SQL. So by default, when we saw that SQL query, we're always getting the first member of the file. But if you really want to work with different members in the file, there's some trickery you can do to create a SQL table alias that then lets you query against those. Like I said, I don't know how often that's used in the real world. We'll just work with a first member since that's where I think people expect the data to live. Now, when we've done that, the data file utility has read the description of that file and created this little data entry program for us. So you see each of our fields here. Now, the reason I didn't make right ascension and declination floating point fields, which could be a reasonable choice in this case for those, distance and light years could also potentially be a floating point field. The only reason I didn't do that is because when I was trying this out earlier, it looks like this DFU does not support working with floating point fields. So I just went ahead and switched those back to zoned decimal, and now they show up in this utility. So this is a very quick and dirty, not particularly user-friendly way of working with data, and we'll see why in a second here. So we can add a couple Messier objects. Let's just start with number one, because where do you start? At the beginning. That's NGC 1952. We can record that. This is the Crab Nebula. Now, distance in light years. It is 6,500 light years away. That's kind of the average of the range that's listed in the catalog. And we defined the distance in light years field to be, I believe, 11 total digits, 2 of which are decimal places. So if I just entered 6,500 here, what the system would end up doing is right aligning this, and it would make the last two positions those 2 decimal points, and everything before it would then be the whole number part. And so I'd end up with 65.0 light years away. And that's not what we want. We want 6,500, 0.00. So what we have to do is right align this. Let's see if it lets me do this. Right, so I have to do it with numbers. So we have to pad this with zeros until we get to the correct spot. So I went a little too far, I think, because that's 65,000. Yeah. All right. This last space here is for the plus or minus sign. So that's why that's there. In this case, it's positive, so we don't need anything. So we we pad it to right align it, leaving 2 decimal positions. So this is 0.00 and then 6,500. So not a user-friendly way to work with data. You would not just generate a program with DFU and hand it over to your end users to start working with your data files. But just to get data in and kind of prove that this is working, this is what we have to work with. Right, so constellation, this is in Taurus. Magnitude, so again, this was magnitude we said was 3 with 1 decimal point. So the magnitude of the Crab Nebula is 8.4, so that would be 0.84. Again, we leave 1 decimal place as the 4, and we have to pad this out so that we get the correct 8 whole number component, and then 0.4, and that last position there is for plus or minus. All right, you're getting the idea here? Right ascension. What did we say here? Well, I know I need to align this all the way out to here. So let's see if I can do this. The right ascension we're going for is 5.575538888 repeating. So we'll round it up to ending on a 9. If I remember correctly, I think I set this up such that we leave ourselves 2 digits in the whole number position. So 0, 5. And then the decimal places, 575538889. And similarly for declination, it's 220145. And then we actually pad the zeros on this side to make this work. So again, in this field, these 2 fields, imagine the decimal point, between character positions 2 and 3. And this one, imagine the decimal point between character positions 2 and 3, and then you'll get these things entered correctly. Right, back up to here, hit enter, and we've created a row in our database. So let's quickly enter one more. I won't talk through it this time like I did the last one. This one doesn't have a common name, so we leave that blank. This one, we need 0.00000. This is 33,000 light years away. So that's 33,000.00, which means I was off by 1 there. That should be right. 33,000.00. Okay. It is in Aquarius. Apparent magnitude is 6.3. And then right ascension is 21.557505556. Declination is 0.82325. Okay. And last but not least, let's jump ahead to Messier 86523 in the NGC catalog. This is the Lagoon Nebula. It is 4,100 light years away. So pad that out to 4,100. And once again, I was off by 1 there, because that's 4,100.00. If I remember how I set this thing up. Constellation, this is in Sagittarius. Apparent magnitude is 6.0. The right ascension is 18.06027777. We'll round that up to 8. And in this case, the declination is minus 24. So we'll do 24, 3, 8, 6, 6, 6, 6, 6, 6, 6, 7, and then the minus sign goes there. I think this is an artifact of both that zoned and packed decimal format where the upper 4 bits of the byte are used as the sign, and the sign of the last byte is the one that counts. So I think this is just a raw sort of representation of the idea that this byte is what is stored. And so you'll have 7 in the lower 4 bits, and you'll have the minus value in the upper 4 bits. And so that's why the minus sign appears with the last digit. Because again, this is just a very sort of literal representation of what's being stored in the file. Okay, so let's exit out of that. We'll say, yes, we're done with data entry. It tells us we added 3. We'll just hit enter here. And now we're back to update data using temporary program. So if I do this away, by the way, now that there's data in it, I can do page up and page down. And you can see it's taken out some of the padding zeros. It's just spaces now. It remembers that that's negative. And so we can see that we did, in fact, successfully save data into this table. And as the last sort of hurrah to finish this up, we'll, again, cheat because we don't really have SQL here. We'll start SQL. And let's say select star for Messier again. And that data that we entered through the DFU utility into the table that we defined with DDS, you can see is available to us in SQL. So those decimal places are now being displayed by SQL. So we can see that we got that correct. We can see we got the magnitudes correct. We got the right ascensions correct. The decimal places are where we expect them. I'll use F20 to move over. And again, the only odd thing here is that even in the SQL view, that minus sign indicating this is negative is still shown at the end. It's not really moving that to the beginning like you're used to seeing, even though it's putting the decimal places in. It's taking off a lot of that extra 0 padding. But nevertheless, that all worked. We defined our data format with DDS. We compiled that to create our physical file to hold the actual table data. And we are able to generate a temporary program using DFU to insert some test data into that table. And then we can prove that all of that data is there and it's available through all of the different data interfaces that the operating system offers, in this case SQL, by going back and querying that data with SQL. So that's it for this video. Thanks for watching. If you want to see more of this, please subscribe, like this video. Like I said, we're also going to have some mainframe content coming up with, in particular, I think we'll start with the old MVS 3.8 version of the IBM mainframe operating system that evolved into OS 390 and ZOS. But right now, we'll have a little bit more fun with the IBM I operating system. Now that we have a table, we can start looking at querying this table without SQL, again, if you don't have the SQL option. We'll look at logical files, which allow you to index these tables differently and create views that perhaps join data from several different physical files. So even without SQL, this is a relational database engine, and you can do all those kinds of queries and joins and data manipulation that you expect from a relational database engine. It's just an interface that is different than SQL. We see DDS, and we'll see the query utility in a future video. So thanks again for watching, and we'll see you again soon.